Welcome, dear students, to this important presentation on a very important topic from electrochemistry, that is pH metry. pH metry is an important part of a very interesting unit of physical chemistry, and so here myself, Dr. S.M. Thorat, Associate Professor from Sri Shivaji College of Arts, Commerce and Science from Akola, Maharashtra, is here with this important presentation. Don't forget to put a like and share this presentation, this video amongst your friends so that they can also get benefited, and also subscribe for getting new concepts. So let's begin. pH metry. Measurement of pH of a solution by constructing a suitable electrochemical cell and measuring its electromotive force, that is EMF, is defined as pH metry. All of us know that pH is the unit of measure that describes the degree of acidity or alkalinity. And we also know that there is a pH scale, that is scale of 0 to 14. pH is defined as negative logarithm to the base 10 of activity of H plus ions. That is, we can write the formula as pH is equal to minus negative logarithm of activity of hydrogen plus ions to the base 10. Now for dilute solution, the activity of H plus ions may be replaced by molar concentration of hydrogen ions, and hence the formula of pH becomes minus negative logarithm of H plus ion concentration to the base 10. pH of a solution can be experimentally determined by combining an indicator electrode, which is reversible to H plus ions, with a reference electrode and measuring the EMF of the cell with the help of potentiometer or pH meter. So here, for determining the pH of a solution, we have to prepare, or we will assemble an electrochemical cell which has an indicator electrode which will be reversible to H plus ions concentration, and that we will combine with a reference electrode and measure the EMF of the complete electrochemical cell with the help of potentiometer or pH meter. Determination of pH of a solution. The potential of a hydrogen electrode depends upon hydrogen ion concentration. That means indirectly the potential of a hydrogen electrode depends on the pH of the solution, as pH of the solution is a measure of hydrogen ion concentration. The hydrogen electrode may act as an anode or as a cathode, depending upon the half cell to which it is connected. When the hydrogen electrode acts as an anode, oxidation occurs according to the following reaction. So this is the reaction in which oxidation is occurring, formation of H plus ions plus electron. Now the concentration effect of this is expressed by taking the example or by taking the help of the Nernst equation. E is equal to E0 minus 2.303 RT divided by N into F log of H plus ion concentration, where we know that these are all constant. 2.303 R is the universal gas constant, T is the temperature, and F is the Faraday's constant. N is the number of electron change which is taking place in the reaction. So according to the this Nernst equation, we can express the concentration, where in this particular Nernst equation, E0 stands for standard electrode potential. What is the standard electrode potential? When the ion concentration is unity, that is 1 molar, we can say, then the electrode potential of that cell becomes the standard electrode potential denoted by E0. So putting the value of E0 as 0, the equation, Nernst equation becomes E is equal to 0 minus 2.303 RT divided by NF into log of H plus ion concentration. Now if you substitute the values of universal gas constant R, the temperature, and Faraday's constant, then for this particular, and substitute the value of N as 1, as there is 1 electron change, so N will be equal to 1. So if you substitute all these values, the factor comes out to be 0.0591. So the equation becomes E is equal to minus 0.0591 into log of H plus ion concentration. But we know that negative logarithm of H plus ion concentration means pH. So the equation becomes E is equal to 0.0591 into pH. And so from this equation, we can determine the pH as E divided by 0.0591. That means if you measure the EMF of the cell, you can get the value of pH of that solution. Now here we are combining the two electrodes, that one is the reference electrode, that is the calomel electrode, and the other is the indicator electrode, that is the platinum electrode. So when the platinum electrode is dipped in the acid solution, and if it is connected with calomel electrode, that is the reference electrode, then the cell can be represented as. So here you can see this is the platinum electrode. Um, Sorry, this is the hydrogen electrode we can say, because this hydrogen electrode is making use of platinum rod. So here we have the setup of the hydrogen electrode where there is a continuous bubbling of hydrogen gas at 1 atmospheric pressure, and the hydrogen electrode contains H plus ion concentration whose concentration is unknown to us, and a platinum electrode is dipped in that solution of H plus ion. So this left hand side from here till here represents the hydrogen electrode, and the right hand side this represents the calomel electrode, that is the reference electrode. These two double lines represent the salt bridge. Okay, with the help of the salt bridge, the two electrodes are connected to each other. So for this particular type of electrochemical cell which we have set up, we can write the EMF of this complete cell as EMF of anode plus EMF of cathode. But EMF of anode, that this is the hydrogen electrode, we know that the EMF of anode, that is hydrogen electrode, comes out to be 0.0591 pH, as we have seen in the earlier slide. And the EMF of cathode, that is the EMF of calomel electrode, the normal value of EMF at room temperature of calomel electrode is plus 0.2415. So putting the value of EMF of calomel electrode and the EMF of this hydrogen electrode, you get this particular equation. Now if you solve this equation in the form of pH, the equation becomes EMF of cell minus 0.2415 divided by 0.0591. So with this particular formula, you can find out the pH of any experimental solution, provided you measure the EMF of that experimental solution. Now since reduction is taking place at the calomel electrode, so the EMF of the calomel electrode is represented as plus 0.2415 volt, expressed as reduction potential. Now let us discuss one of an important aspect, that is the change of potential with concentration. When a metal is dipped in a solution containing its own ions, it passes into the solution in the form of ions, and the electrons are liberated at the electrode. So because of this, a potential difference is set up between the metal electrode and the interface, that is the solution in which that metal electrode is dipped. The potential difference for the electrode reaction according to the Nernst is reduced state in equilibrium with oxidized state plus n electron. That means if you represent the reduced state as M, it is in equilibrium with Mn plus, that is the oxidized state, plus n electron. Now again applying the Nernst equation to this, we can express it as EMF of the cell E is equal to E0 plus RT divided by NF into ln, that is log to the base E, activity of Mn plus divided by activity of reduced state of the metal. This is the activity of oxidized state and this is the activity of the reduced state. So the equation becomes E is equal to E0 plus RT divided by NF log to the base E, oxidized state divided by reduced state, that is the concentration of oxidized activity or concentration of oxidized state divided by reduced state. Now here if you change this log, which is to the base E, to the log to the base 10, then you have to multiply by the factor 2.303, and if you substitute the value of 2.303 RT divided by F, the factor comes 0.0591, and this is this is the number of electron which undergoes the change here. So E is equal to E0, the formula becomes E is equal to E0 plus 0.0591 divided by N log of oxidized state divided by reduced state. Now if you want to put this reduced state to the numerator and oxidized state to the denominator, then here you will have to put a minus sign. The equation becomes E is equal to E0 minus 0.0591 divided by N log of reduced state divided by oxidized state. Now, even though the standard electrode potential is fixed, the concentration of an ion in a half cell affects its single electrode potential. And this particular part, it is given or expressed in the form of the Nernst equation. E is equal to E0 minus 2.303 RT divided by NF log of concentration of iron. That is, whatever is the concentration of iron, log of concentration of iron, that represents, and this is the Nernst equation which represents the EMF of the half cell. Substituting the value of all this constant, that is 2.303 R the gas constant, T the temperature in degrees Kelvin, and F is the Faraday's constant 96500 coulombs. Okay, this particular factor we know the value is 0.0591 divided by N log of concentration of iron. So this shows that for a half oxidation potential, if suppose you take the metal electrode zinc in equilibrium with Zn plus electrode, it changes with the concentration of zinc sulfate solution. This is the equation cell in which the oxidation occurs. And if you have to express it for reduction reaction, the sign of EMF will be reverse. So here it will be minus sign in front. So E is equal to minus E0 plus 0.0591 divided by N log of concentration of ion. The potentials of electrodes having more tendency of ionization than standard hydrogen electrode are given a positive sign, and the potential of electrodes having less tendency of ionization than the hydrogen are given a negative sign. So this particular sentence is very important. Now we'll discuss the types of cells. In voltaic cells, two half cells are combined, and therefore the total EMF, the net EMF of the cell, is the algebraic sum of the two half cells. That means the total EMF of the complete electrochemical cell is equal to the addition of EMF of two half cells. The voltaic cells are generally divided into two types, chemical cell and concentration cell. Now, what is the chemical cell? The cell in which the chemical energy converts into electrical energy is called as chemical cell. Daniell cell is the best example of chemical cell. Zinc rod dipped in zinc sulfate solution and copper rod dipped in copper sulfate solution. Okay, this is an example of a Daniell cell. The net cell reaction can be written as Zn dipositive ion plus copper is equal to Zn plus copper 2 plus. And if you want to write the cell representation of this particular chemical cell, you can write zinc rod in contact with zinc sulfate solution, which is in equilibrium with copper sulfate solution, in which the copper electrode or copper rod is dipped. So this is the complete representation of such a type of chemical cell. Now we will discuss the concentration cell. If the potential difference is produced because of different concentration of the same electrolyte. Now here we are not going to take two different type of electrode, that is zinc electrode or copper electrode, but we will take only one type of electrode, that is the zinc electrode, but we are going to take two type of solution, that is we are going to utilize two different type of concentration solution. So this type of cell when we form is called as the concentration cell. That means we are going to use the same electrolyte, but we are going to prepare two different solution, that is concentration. One is 0.1 molar zinc sulfate solution and the other half cell will contain 1 molar zinc sulfate solution. That means the electrolyte is same, but the two half cells are prepared in such a way that one will contain 0.1 molar solution, the other will contain 1 molar zinc sulfate solution. So for example, zinc plate dipping in 0.1 molar zinc sulfate solution is considered as one half cell, whereas the zinc plate dipping in 1 molar zinc sulfate solution is another half cell. And if these two half cells are combined, then at electrode with low concentration, ionization will take place. So zinc ionizing into Zn plus ion plus 2 electron, that is the oxidation. And at electrode with higher concentration, an opposite reaction will take place, that is the reduction. So Zn2 plus ion plus 2 electron giving metallic zinc, that is the reduction. How we will represent the electrochemical cell? The electrochemical cell can be represented by zinc in equilibrium or in contact with 0.1 molar zinc sulfate solution, which is in equilibrium with again zinc sulfate solution, but which is of 1 molar solution, and in which the zinc plate is dipped. So this is type of concentration cell which is made by using same electrolyte but of two different concentration that form the two different half cells. Now coming to the our experimental determination of pH of the solution using hydrogen electrode. Now first we will discuss the construction of hydrogen electrode. Here you can see the construction of the hydrogen electrode. The hydrogen gas electrode, it is reversible with respect to H plus ions, and hence it can be used as an indicator electrode for pH measurement. Okay, as it will indicate the change in the potential of the hydrogen ions, the hydrogen electrode is called as indicator electrode, which can be used for pH measurement. Now, what is the construction of this hydrogen electrode? It consists of a small strip of platinum metal. Here you can see, which is activated by coating with the platinum black. The platinum foil is welded at the end of a platinum lead fused in a glass jacket, provided with a side tube. This is the side tube for the entry of the pure hydrogen gas, which should be at 1 atmospheric pressure. This platinum electrode is immersed in the solution of which we have to determine the pH. And the pure hydrogen gas at 1 atmospheric pressure is bubbled across the surface of the platinum foil in such a manner that this particular hydrogen electrode, it is continuously in contact with both the solution as well as the gas. So this is the construction of hydrogen electrode. The platinum foil, we can say, or a strip of platinum metal which is platinized or which is coated with platinum black, and it is fused to this platinum wire. Okay, here you can see it is fused. The glass tube is sealed at the one end, and here this is the side tube from which there should be arrangement of hydrogen gas. And this particular hydrogen electrode we can connect to, here it is shown connected to the high resistant voltmeter, or you can connect it to the pH meter. And this particular beaker contains 1 molar hydrochloric acid solution, or you can take your experimental solution of which you have to determine the pH. Now coming to the half cell reaction of this and single electrode reduction potential, twice H plus 2 electron gives H2 gas at 1 atmosphere. Now remember, platinum does not take part in the electrochemical reaction, and it is only acting as the site for the transfer of electrons. The reduction potential of this hydrogen electrode is given with the help of Nernst equation. We can write the reduction potential E is equal to E0 minus 2.303 RT divided by NF log of pressure of hydrogen gas divided by H plus ion concentration. Since two H plus ion concentrations are involved, here you have written H plus ion concentration raised to the power 2. For this type of electrode, E0, that is the standard electrode potential of hydrogen, is taken as 0.0 volt by convention. The value of N in this particular equation, that is since there is a 2 electron change, the value of N is 2. Pressure of hydrogen gas is 1 atmosphere. At 25 degrees centigrade, the value of 2.303 RT divided by F, we know it comes out to be the factor 0.0591, and if you put it in this particular, the equation becomes the electrode potential, it is given by E is equal to 0. Since the value of this standard electrode potential E0 is 0 minus 0.0591 divided by 2, since there is 2 electron change, so here you have written 2 log of, put the pressure of hydrogen gas as 1 atmosphere, so we have written 1, and divided by H plus ion concentration raised to the power 2, since 2 hydrogen atoms are involved, here we have written 2. Now if you solve this particular equation, minus 0.0591 divided by 2 multiplied by, now if you take this hydrogen plus H plus ion concentration raised to the power 2 in the numerator, then it will become minus sign. That minus sign is written in front. So minus 2 log of H plus ion concentration. Now this 2 will get cancelled, and we know that this equation becomes 0.0591 log of H plus ion concentration. But we know that if you put a minus sign here, minus log of H plus ion concentration is equal to pH. So the equation becomes E is equal to minus 0.0591 into pH, as pH is equal to minus negative log of hydrogen ion concentration. Now, what is the method? How can you measure the EMF of the solution by using the hydrogen electrode? The pH of the solution can be determined by coupling the hydrogen electrode, okay, and putting it in the solution of which the pH is unknown to us, and uh, it is combined with another normal hydrogen electrode, which is considered as primary reference electrode by KCl salt bridge. The function of this salt bridge is to eliminate the liquid junction potential. So see here we can represent the electrochemical cell. Here we have set up two half cells. Both of these two half cells are hydrogen electrode. Okay. One hydrogen electrode is a standard hydrogen electrode whose concentration is 1 molar, and another is the hydrogen electrode which is dipped in the solution of which the concentration is unknown to us. So here you can see both these two, the left hand side electrode as well as the right hand side electrode, both these two electrodes are hydrogen electrode. The EMF of this cell is determined with the help of potentiometer, because potentiometer is an instrument by which you can measure the EMF, as well as there is a provision of measuring the pH with the help of potentiometer. As hydrogen electrode involving solution of unknown H plus ion concentration is connected to a standard hydrogen electrode, the EMF of this complete resulting electrochemical cell is given as E cell is equal to EMF of right hand electrode. This is the right hand electrode. So EMF of right hand electrode minus EMF of left hand electrode. If you substitute the value of EMF of right hand electrode as 0.0 minus EMF of left hand electrode, that is known 0.0591 into pH at 25 degrees centigrade. So here the equation becomes EMF of cell is equal to 0.0591 pH, or pH can be written as calculated as E cell divided by 0.0591. So that's simply by measuring the EMF of the cell. Here in the formula, if you measure the EMF of the cell with the help of potentiometer at 25 degrees centigrade, you can calculate or you can find out the pH of the experimental solution. Now, what are the advantages of hydrogen electrode? It can be used over the entire pH range. It is highly accurate. It does not exhibit salt error. It has low internal resistance, and hence ordinary potentiometer can be used for EMF measurement. What are the disadvantages of using hydrogen electrode? It cannot be used in a solution containing ions of metals that are below the hydrogen in the electrochemical series. What is electrochemical series? Arrangement of elements in increasing order of reduction potential values. Interaction with the hydrogen will occur and the metal will be deposited on the electrode surface. The platinum metal, the platinum black in the hydrogen electrode coating deteriorates. Okay, and hence it should be renewed from time to time. Okay, remember we have coated the platinum foil or a piece of platinum metal with the help of platinum black, and this coating platinum black is getting washed out, deteriorating, and hence it has to be renewed from time to time. And if in your solution, if you have the impurities, then that will also poison the platinum black foil. And it is not easy to get the pure and dry hydrogen gas. It is difficult to maintain the pressure of the hydrogen gas at a fixed value, that is 1 atmosphere, due to mechanical difficulties. So it cannot be used in presence of oxidizing and reducing agents. So this is all about the advantages and disadvantages of hydrogen electrodes. So to overcome these disadvantages, we can determine the pH of a solution by using a more profitable electrode, that is the quinhydrone electrode. This particular electrode was introduced by the scientist E. Billman in the year 1921. Many of the experimental difficulties can be overcome. It can be removed by the use of this electrode. Quinhydrone is a 1:1 molecular compound of quinone, represented by Q, and hydroquinone, represented by H2Q. And in solution, it provides equimolecular quantities of these two substances. So let us discuss the construction and how to measure the single electrode potential, again reduction potential of this quinhydrone electrode. The quinhydrone electrode may be set up easily by adding a pinch of quinhydrone to the solution whose pH we have to determine. That is, in our experimental solution, you have to add a pinch of quinhydrone powder. A bright platinum electrode, it is kept or it is immersed in the solution to establish the electrical contact. Now here you can see the construction of this quinhydrone electrode. quinone, hydroquinone and hydrogen ions. Here you can see quinone, hydroquinone and hydrogen ions form a reversible redox system. With the help of the following cell reaction, here you can see the reversible redox reaction. This is the quinone in contact with hydrogen ion concentration in contact with 2 electron gives hydroquinone, or in short we can represent the quinone as Q and hydroquinone as H2Q. Here you can see the structure of quinone Q and hydroquinone. Okay. The reduction potential of the quinhydrone electrode, again it is given by the Nernst equation. E is equal to E0Q minus 2.303 RT divided by NF log of concentration of hydroquinone, that is H2Q, divided by concentration of quinone into concentration of H plus ions raised to the power 2. Now for this particular type of electrode, again this is the standard electrode potential. Quinhydrone potential standard electrode value is 0.6996 volt at 25 degrees centigrade. There is a 2 electron change, so value of 2 is 1, so value of n is 2. The value of n, that is the number of electron change, is 2, and at 25 degrees centigrade we know the 2.303 divided by RT divided by NF, the value is 0.0591. Now in aqueous solution of quinone and hydroquinone, that is quinhydrone, the concentration of this hydroquinone and quinone, these two concentration are same. So here the concentration of hydroquinone and quinone, this is same. Okay, so the equation becomes 1 divided by H plus raised to the power 2. And if you rearrange this particular equation, EQ is equal to 0.6996 minus 0.0591 divided by 2 multiplied by 2 into minus log of hydrogen ion concentration, and the equation becomes EQ is equal to 0.6996 minus 0.0591 into pH as minus log of H plus ion concentration, that is pH. So this is the particular equation. With the help of that you can measure the reduction potential of quinhydrone electrode, and this we have found out by Nernst equation. Thus reduction potential of quinhydrone electrode is a function of pH of the solution. That means if you find out the this reduction potential value, if you measure the reduction potential value of quinhydrone electrode, you can find out the pH of the experimental solution. Now what is the method? The pH of the solution can be determined. Again you have to couple the two electrode by coupling the quinhydrone electrode with a reference electrode, secondary reference electrode. We are using calomel electrode with the help of a salt bridge, and the complete electrochemical cell is set up, and it is represented as here. To the left hand side we have the calomel electrode, that is mercury in contact with mercurous chloride solid, and that is the calomel electrode is filled with saturated KCl solution. So this is the construction of calomel electrode. Okay, it contains the mercury, liquid mercury in contact with a paste of mercurous chloride, and the upper part of the glass tube is filled with saturated KCl solution. And this right hand side is a quinhydrone electrode. Okay, that is quinone and hydroquinone both taken. It forms quinhydrone. You have to put a pinch of quinhydrone powder into the solution of that of which we have to measure the pH. So this is the solution, experimental solution, which contains H plus ion. That means you have to measure the pH of this solution. Okay, this is the construction of the quinhydrone electrode, which is made by inserting a platinum electrode or platinum rod in experimental solution in which we have put a pinch of quinhydrone. In this cell, the oxidation takes place on the calomel electrode, whereas the reduction takes place at the quinhydrone electrode. And using the reduction electrode potential values, we have the EMF of the complete electrochemical cell. We can write as E cell is equal to EMF of quinhydrone electrode, that is the right hand electrode, minus EMF of calomel electrode, that is the left hand electrode. Now we know that the EMF of quinhydrone electrode, just now we have found out in the previous slide, that is 0.6996 minus 0.0591 pH volt. And the EMF of calomel, we know at 25 degrees centigrade, the EMF of calomel, the value is 0.2415 volts. So if you substitute both these two values in this particular equation, the equation becomes EMF of the complete electrochemical cell is equal to 0.6996 minus 0.0591 pH minus the EMF of calomel, that is 0.2415. The final equation becomes pH is equal to 0.4581 minus E cell, that is EMF of the complete cell, divided by 0.0591. That means if you measure the EMF of the complete electrochemical cell here which you have set up, you can get an idea or you can get the value of pH of that experimental solution. So this is the complete methodology. And what are the advantages of quinhydrone electrode? It is very simple to set up, as we only have to put a pinch of quinhydrone to our experimental solution, and it gives accurate values of pH because equilibrium is attained quickly. Small quantity of solution is sufficient for pH measurement. It gives accurate results even in presence of oxidizing ions. It can be used for measuring the pH of the solution containing Zn dipositive ion, lead, copper, etc., where hydrogen electrode is unsuitable. Ordinary potentiometer can be used for EMF measurement. Now, what are the disadvantages? It cannot be used in alkaline solution, that is above pH is equal to 8, because the hydroquinone H2Q acts as a weak diabasic acid in more alkaline solution. So, if you use a solution, alkaline solution whose pH is above 8, then this particular quinhydrone electrode becomes, it is not possible to use the quinhydrone electrode. Atmospheric oxygen slowly oxidizes H2Q, that is hydroquinone, and therefore the hydroquinone should be freshly prepared. The potential of this electrode is affected by even small concentration of neutral salts. So because if the neutral salts are there, then the salt error will come up. Now we will determine the pH by using the third type of electrode, that is here we are going to use a glass electrode. Now when two solutions of different pH are separated by a glass membrane of low melting point and high conductivity glass, potential is developed across the membrane. Okay, this is the concept of glass electrode. When such a glass bulb is filled with 0.1 molar HCl solution and it is immersed, it is put in another solution containing H plus ions, the potential of such electrode depends on the pH of the outer solution in which that glass electrode is dipped. Thus, such a glass electrode can be used for the measurement of pH of outer solution. Now the construction of glass electrode and how to measure the single electrode potential. Again, glass electrode is made of a thin glass bulb or a special quality glass which is attached to a glass tube. The glass bulb is filled with 0.1 molar HCl solution and a silver wire coated with silver chloride, or you can also use a platinum wire. It is immersed in it. Single electrode potential of a glass electrode is given by Eg is equal to E0G plus 0.0591 into log of H plus ion concentration. We can write the equation as Eg is equal to E0G minus 0.0591 into pH, where this particular E0G, it is a constant for the given glass electrode and is called as a symmetry potential. Value of this E0G, that is a constant, it may be determined using the buffer solution of known pH. Okay, so you can find out the value of this standard glass potential by using a buffer solution of known pH. Now, what is the method? Glass electrode is dipped in a solution of unknown pH and it has to be coupled or it has to be combined with the reference electrode like calomel electrode. Again, here we are going to combine the two half cells. One is the reference electrode, the calomel electrode, and the other is the glass electrode which is dipped in the solution of which you have to find out the pH. Both these two electrodes are connected to an electronic potentiometer or pH meter. The pH meter displays a pH scale, pH from 0 to 14, and hence we can directly read the pH of the unknown solution. That means if we are using a pH meter, or there is a also facility in the potentiometer, with the help of that also you can find out the, or you can measure the pH. The pH scale, you know, all of you know the pH scale ranges from 0 to 14, and before taking this measurement, you have to condition the glass electrode. Glass electrode must be conditioned, and pH meter you have to calibrate using the buffer solution of known pH. Commonly pH is, the solution of common pH is 4 and pH 9. So the glass electrode has to be conditioned and the pH meter has to be calibrated by using two buffer solution. One is the buffer solution of pH 4 and other is the buffer solution of pH 9. The cell which is represented here, we are going to form again the two half cell. One is the calomel electron, the other is the glass electrode. So we are going to set up a complete electrochemical cell containing two half cells. So here you can see the two half cell. On the left hand side is the glass electrode, which is made by silver electrode dipped in HCl solution, and in the bulb of the glass electrode you have to take 0.1 molar HCl solution. And this glass electrode is dipped in the solution of which you have to find out the pH or unknown solution. And to this right hand side you can see the calomel electrode. Okay, mercury, liquid mercury in contact with mercurous chloride in fused solid state, and that is filled with saturated KCl solution. Again here the two double lines here, it represent the salt bridge. Or if platinum electrode is used in glass electrode, platinum wire is used, then you can represent the glass electrode as platinum wire in contact with 0.1 molar HCl solution, and this is the experimental solution. And to the right hand side we have the calomel electrode, which is the reference electrode. The EMF of this complete cell is given by the equation E cell is equal to EMF of right hand side minus EMF of left hand side. The right hand side is the calomel cell and the left hand side is the glass electrode. We know that EMF of calomel electrode at 25 degrees centigrade is 0.2415, and the EMF of the glass electrode we have found out, that is EMF of glass electrode is E0G minus 0.0591 pH, where E0G is the asymmetry potential, okay, whose value you have to determine. So the complete, if you put the value of these two, EMF of calomel and glass, the equation becomes EMF of the complete electrochemical cell is equal to, substitute the EMF of calomel at 0.2415 and substitute the EMF of glass electrode. So this is complete EMF of glass electrode is 0G minus 0.0591 pH. If you solve this complete equation, the final equation comes pH is equal to E cell, that is EMF of the complete cell, minus 0.2415 plus E0G divided by 0.0591. So this is the complete the last formula to calculate the pH by using the glass electrode. By using the above formula, we can determine the pH of unknown solution, okay, using the combination of glass electrode and saturated calomel electrode. And here we have a diagram or a diagrammatic representation showing the two half cells. This is the right calomel electrode. Here you can see the, here this is the liquid mercury, the dark black portion. This is the liquid mercury, and below that there is a paste of mercury plus mercurous chloride, okay, and above this, inside this tube is filled the KCl saturated solution, okay. This is the side knob for, with the, from here you can put the saturated KCl solution in this glass tube, okay, which is sealed here. And this is the side tube again, which can be put in this beaker, or here you can also use a salt bridge. Okay, now this beaker contains the solution of unknown pH, that is the experimental solution of which you have to determine the pH. So in this beaker we have taken the solution of which you have to determine the pH, and here you have inserted another electrode, that is the glass electrode. Here you can see this is the platinum wire, okay, and inside the bulb, that is a 0.1 molar HCl solution. Again it is sealed at these two, and these two here they can be shown connected to the vacuum tube, okay. Both these two are platinum wire, or here you can connect it to a potentiometer or pH meter. So this is the diagrammatic representation of glass electrode as well as the calomel electrode, that is the complete electrochemical cell as we have discussed in the answer. Now, what are the advantages of glass electrode? It may be used in the presence of strong oxidizing, reducing or alkaline solution. It can be used for solution having pH values 2 to 10, with some special glass values can be extended up to 12. It is simple to operate, it is immune to poisoning, it has no salt error or protein error, and the equilibrium is reached quickly. It can be used in colored, turbid or colloidal solution also. Now there are some disadvantages also in glass electrode. The glass bulb is very delicate, it is very fragile, and it has to be handled with very care. Therefore it has to be used with great care, as the glass membrane has a very high electrical resistance. Hence it cannot be used with ordinary potentiometer, and it cannot be employed in the solution. It cannot be used with the solution that is pure organic solvent like ethyl alcohol, acetic acid or gelatin. So these are some of the advantages and disadvantages of the glass electrode, and that come to the end of this presentation on pH metry. So Here in this particular presentation, we have discussed the concept of pH metry, and we have explained how to measure the pH of the solution by using three kinds of electrode. First is the hydrogen electrode, second the quinhydrone electrode, and third by using the glass electrode. So by using all these three types of electrode, you can measure the pH of the experimental solution, and this particular technique is called as pH metry. Hope you understood everything. Thank you.